For 2 decades, China watched American laser weapon programs burn through billions with nothing to show but laboratory experiments and PowerPoint presentations. Every prototype failed in the field, every deadline slipped, every test fell short of operational requirements. Beijing's state media ran gleeful headlines about the fantasy weapons that could not hit their targets, could not handle bad weather, and could not survive a real battlefield. Chinese generals dismissed directed energy as a Western distraction, a technological dead end that diverted resources from proven kinetic systems. The message was clear. While America chased science fiction, China was building real missiles, real hypersonics, and real air defenses that actually worked. Then, in the skies above Israel and on test ranges in New Mexico, everything changed. The iron beam system did not just work, it vaporized threats at the speed of light with a precision and cost efficiency that made every missile-based defense obsolete overnight. What had been dismissed as perpetual vaporware suddenly became the weapon that could render China's entire missile arsenal irrelevant. How did a technology that failed for decades suddenly leap from concept to combat ready? And why did the system that Beijing mocked as impossible become the one that rewrote the entire calculus of modern warfare? In the early 2000s, the United States poured money into directed energy research with the kind of optimism usually reserved for Manhattan Project-scale breakthroughs. The airborne laser program mounted a megawatt-class chemical laser in a modified Boeing 747, creating a flying death ray meant to shoot down ballistic missiles during their boost phase. The concept was elegant. Catch missiles when they are most vulnerable, moving slowly and spewing hot exhaust, and burn through their casings with concentrated light. The price tag was $5 billion. The result was a system so complex, so maintenance-intensive, and so limited by atmospheric conditions that it never achieved operational status. In 2014, the program was quietly terminated, the aircraft sent to the boneyard, and the dream shelved. The Navy tried next with the Laser Weapon System, or LAWS, mounted on the USS Ponce in the Arabian Gulf. The 30-kilowatt system could burn through drone airframes and disable small boats, generating headlines about the dawn of a new era in naval warfare. But the limitations were glaring. The laser needed perfect weather, clear skies, and calm seas. Humidity scattered the beam. Rain absorbed its energy. Dust and smoke rendered it useless. In operational testing, the weapon worked only in ideal conditions, the kind of conditions that rarely exist in actual combat. By 2020, LAWS had been removed from service, replaced by conventional weapons that worked regardless of the weather. Chinese military observers watched these failures with satisfaction. Articles in People's Liberation Army journals cataloged every setback, every cost overrun, every missed promise. One widely circulated 2017 analysis dismissed directed energy weapons as technologically immature and operationally impractical. The author argued that laser systems would never overcome the fundamental physics problems: atmospheric attenuation, thermal blooming, and the massive power requirements needed to generate militarily useful beam strength. The conclusion was dismissive. The United States, it said, was wasting money on weapons that sounded impressive but could not deliver when it mattered. Beijing's confidence was not baseless. Their own research into directed energy had stalled for the same reasons. Chinese scientists understood the challenges: generating enough power, managing the heat, keeping the optics clean, and maintaining beam coherence over operationally relevant distances. The consensus was that these problems were decades away from practical solutions. Better to invest in proven technologies like hypersonic glide vehicles, anti-ship ballistic missiles, and advanced air defense systems. Those weapons work today, not in some hypothetical future. Western critics echoed some of those concerns. Defense analysts questioned whether directed energy would ever escape the laboratory. Congressional hearings featured skeptical lawmakers demanding to know why taxpayers were funding laser programs that never seemed to reach deployment. Even within the Pentagon, voices argued for redirecting funds to conventional systems with proven track records. The directed energy community found itself constantly defending not just individual programs, but the entire concept. But while the headlines focused on failures, a quieter revolution was underway. The problem had never been the physics. Lasers could destroy targets, that much was proven in controlled tests. The problem was engineering, building a system compact enough, powerful enough, and reliable enough to operate in the chaos of real combat. Solving those problems required breakthroughs in solid-state laser technology, thermal management, and beam control. Those breakthroughs were coming, not from massive defense contractors, but from a mid-sized Israeli company working in the shadow of constant missile threats. Rafael Advanced Defense Systems, the Israeli firm behind the Iron Dome, understood something that eluded larger programs. The key was not building the most powerful laser possible. It was building a laser powerful enough to do the job at a price the military could afford to field in numbers. Iron Dome had proven that missile defense could work, but each interceptor cost between $40,000 and $100,000. Against cheap rockets and drones, the economics were unsustainable. Shoot down a $500 drone with a $100,000 missile, and the attacker wins by bankrupting the defender. Rafael needed a solution that flipped that equation. The answer was Iron Beam, a 100-kilowatt fiber laser system designed to engage rockets, mortars, drones, and cruise missiles at ranges up to several kilometers. The breakthrough was in the architecture. Instead of one massive chemical laser or a cumbersome free electron laser, Iron Beam uses multiple solid-state fiber lasers combined into a single coherent beam. Each fiber module generates a portion of the total power, and if one fails, the others keep working. The system is scalable, reliable, and far easier to maintain than earlier designs. The laser itself is invisible to the naked eye, but its effects are instant and devastating. When Iron Beam locks onto a target, the beam focuses on a single point, heating the surface to thousands of degrees in seconds. Metal warps. Structural components fail, and the target either disintegrates or tumbles out of control. There is no explosion, no shrapnel, just the sudden collapse of whatever the beam touched. The engagement happens at the speed of light, meaning there is no time for the target to maneuver or deploy countermeasures. By the time the missile or drone realizes it is under attack, it is already falling. The power requirements were solved with advances in commercial laser technology. Fiber lasers, originally developed for industrial cutting and welding, had become far more efficient over the past decade. What once required massive generators could now run off the electrical system of a standard military vehicle. Iron Beam's power source is a mobile diesel generator, the same kind used for field hospitals and command posts. The system can operate continuously as long as fuel is available, a stark contrast to missile-based defenses that run out of interceptors after a few dozen shots. Thermal management was another critical breakthrough. High-power lasers generate enormous amounts of waste heat. Early systems overheated after just a few shots, requiring long cool-down periods. Rafael's engineers developed a closed-loop cooling system that dissipates heat fast enough to allow continuous firing. In tests, Iron Beam engaged multiple targets in rapid succession without degrading performance, proving that the weapon could sustain fire rates necessary for real combat. The beam control system is equally sophisticated. Atmospheric conditions, wind, humidity, and temperature gradients all distort laser beams, reducing their effectiveness at range. Iron Beam uses adaptive optics, essentially a deformable mirror that adjusts in real time to compensate for atmospheric distortion. Sensors measure how the beam is bending, and the mirror reshapes itself thousands of times per second to correct the path. The technology is borrowed from astronomy, where adaptive optics allow ground-based telescopes to see clearly through the turbulent atmosphere. Applied to weapons, it means Iron Beam can maintain a tight, focused beam even in less than ideal conditions. The first live fire test took place in 2014 at a range in southern Israel. The target was a small drone similar to the kind used by Hamas and Hezbollah for reconnaissance and harassment. The Iron Beam system tracked the target, locked on, and fired. Within seconds, smoke poured from the drone's body and it tumbled to the ground. The test was repeated with mortar rounds, crude rockets, and even artillery shells in flight. Every engagement was successful. The beam hit, the target fell, and the system reset for the next shot. By 2022, Iron Beam had progressed from prototype to operational testing. The Israeli Defense Forces deployed the system to field units, integrating it with Iron Dome batteries to provide layered defense. Iron Dome handled long-range threats with interceptors, while Iron Beam engaged close-in targets with the laser. The combination proved devastatingly effective. During a series of rocket attacks from Gaza, Iron Beam intercepted dozens of projectiles, each one destroyed for the cost of a few dollars worth of diesel fuel. The economic revolution was complete. Defense had become cheaper than offense. The system's modularity is another force multiplier. Iron Beam can be mounted on trucks, installed on ships, or placed on fixed defensive positions. Each unit operates independently or as part of a networked defense, sharing targeting data with radars and other sensors. In a scenario where hundreds of drones or missiles saturate a defensive zone, multiple Iron Beam systems can engage simultaneously, each one taking targets as fast as the beam can slew and fire. The coordination happens automatically, managed by AI algorithms that assign targets based on threat priority and engagement geometry. The psychological impact on adversaries is profound. For years, militant groups and hostile states relied on overwhelming defenses with cheap, mass-produced weapons. Fire enough rockets, and some would get through. Iron Beam eliminates that calculus. Each rocket is intercepted at a cost so low that the attacker cannot win through volume. The defender can shoot all day, every day, without running out of ammunition. The only limit is fuel, and fuel is cheap and abundant. Chinese military analysts watched the Iron Beam tests with growing alarm. Internal assessments leaked to Western intelligence revealed a strategic recalibration underway. The weapon they had dismissed as fantasy was now operational, and its implications extended far beyond the Middle East. If Iron Beam could shoot down rockets and drones, it could be scaled to engage cruise missiles, hypersonic glide vehicles, and even ballistic missile warheads. The technology that China had bet against was suddenly the technology that threatened to neutralize their most advanced offensive systems. The cost per kill metric is where Iron Beam becomes a strategic game changer. Traditional missile interceptors are a zero-sum game. Each launch depletes the magazine, and reloading takes time and money. Iron Beam fires for as long as the generator runs, and each shot costs roughly $2 to $3 worth of electricity and cooling. That is not a typo. A weapon that destroys million-dollar missiles for the price of a cup of coffee. The exchange ratio is so lopsided it breaks every assumption about how defense economics work. China's anti-access strategy relies on saturating American and Allied defenses with missile barrages. Launch 100 DF-21s and DF-26s at a carrier group, and even if 90% are intercepted, the remaining 10% do catastrophic damage. That calculus assumes the defender has a limited number of interceptors, each costing millions. Iron Beam rewrites the math. A carrier group equipped with laser defense systems can engage every incoming missile without worrying about running out of shots. The saturation attack, the cornerstone of Chinese naval doctrine, becomes a waste of expensive hardware. The implications extend to air defense as well. China has invested heavily in cruise missiles, designing them to fly low and fast, hugging terrain to avoid radar detection. The DF-100 and YJ-18 are formidable threats, capable of striking targets hundreds of miles away with precision. But cruise missiles are fundamentally vulnerable to directed energy. They fly predictable paths, their airframes are lightweight, and they have no countermeasures against lasers. An Iron Beam-equipped destroyer or ground installation can engage cruise missiles as soon as they come over the horizon, burning them out of the sky before they reach terminal attack range. The United States military has taken note. In 2023, the Army began field testing a variant of Iron Beam adapted for American systems, designated the High Energy Laser Tactical Vehicle Demonstrator. The platform integrates a 100-kilowatt laser onto a Stryker armored vehicle, providing mobile air defense capable of engaging drones, helicopters, and incoming rockets. Initial tests at White Sands Missile Range exceeded expectations, with the system destroying multiple targets in rapid succession without degradation. The Navy is pursuing similar capabilities. The Layered Laser Defense Program aims to equip destroyers and cruisers with high-energy lasers capable of engaging anti-ship missiles and aircraft. The goal is to field systems by the late 2020s, creating a defensive layer that complements traditional missile interceptors. Combined with Aegis radar systems and advanced tracking, laser-equipped warships could create defensive bubbles that are nearly impenetrable to conventional missile attacks. Allied nations are following suit. The United Kingdom, Germany, and Japan have all initiated directed energy programs, many of them in partnership with Rafael or American defense contractors. The goal is not just to acquire the technology, but to integrate it across coalition forces. In a Pacific conflict, that interoperability could prove decisive. Allied fleets and ground units equipped with laser defenses create a networked shield that extends across the theater, denying China the ability to overwhelm any single point through volume. The strategic shift is seismic. For decades, offense dominated defense. Missiles were cheaper and more effective than the systems designed to stop them. Iron Beam inverts that relationship, making defense not just viable, but economically sustainable. The attacker now faces a dilemma: invest billions in missiles that will be destroyed for pennies, or accept that entire classes of weapons have been rendered obsolete. Chinese engineers are scrambling to adapt. Discussions in People's Liberation Army research institutes focus on countermeasures, reflective coatings to deflect laser energy, ablative materials that shed heat, and spinning projectiles that distribute beam impact across the surface. But each solution adds weight, complexity, and cost, undermining the economic advantage that made mass missile attacks viable in the first place. A $1 million missile that needs $500,000 in laser-resistant modifications is no longer a cost-effective weapon. Beijing's response has been to accelerate hypersonic development, betting that weapons moving at Mach 5 or faster will be too quick for lasers to engage. But even that assumption is questionable. Iron Beam's engagement cycle, from detection to destruction, takes only a few seconds. A hypersonic glide vehicle, despite its speed, still has to pass through the laser's engagement envelope. If the beam locks on, speed becomes irrelevant. The target cannot outrun light, and the structural stresses of hypersonic flight make the airframe more vulnerable to thermal damage, not less. The real revolution is in the shift from kinetic to energy-based defense. Kinetic interceptors, missiles hitting missiles, are limited by the laws of physics. They need time to launch, accelerate, and intercept. They have finite quantities. Directed energy has none of those limitations. The only constraint is power, and power is renewable. As long as the generator runs, the weapon fires. That endurance changes how wars are fought, shifting the advantage decisively to the defender. One retired U.S. Air Force general, speaking at a 2024 defense symposium, described Iron Beam as the weapon that closes the kill chain faster than the enemy can open it. He explained that modern warfare is about compressing decision cycles, acting faster than the adversary can react. A laser weapon that engages at the speed of light collapses that cycle to near instantaneous. The enemy fires, and before the missile reaches its target, it is already destroyed. There is no time for second chances, no opportunity to adapt. The engagement is over before it begins. The psychological dimension is equally potent. For years, adversaries have relied on the threat of missile barrages to deter intervention or coerce concessions. The implicit bargain was simple: back down or face overwhelming firepower that your defenses cannot handle. Iron Beam breaks that bargain. The missile barrage is no longer overwhelming. It is just expensive noise absorbed by defenses that never run dry. The coercive power of missiles evaporates when the target can shoot down everything you throw at it for the cost of running a generator. China's mockery has turned to silence. State media, once eager to ridicule American laser programs, now publishes sober assessments of directed energy threats. The tone has shifted from derision to concern, acknowledging that what seemed like science fiction is now operational reality. Some Chinese analysts openly admit that the directed energy revolution caught Beijing off guard, and catching up will require years of research and investment. The United States is not waiting. Production contracts for laser systems are expanding, with multiple contractors developing systems at various power levels. The goal is to field directed energy weapons across the joint force, from individual vehicles to entire fleets, creating a layered defense that is resilient, scalable, and economically sustainable. By the end of the decade, lasers could be as common on military platforms as radar systems are today. Right now, Iron Beam systems sit on the borders of contested regions, scanning the skies for threats. Each one represents a paradigm shift in how defense works. The weapon that was dismissed as impossible, that failed for decades, has finally arrived, and it brought with it a capability that makes the offensive systems China spent billions developing look like relics of a bygone era. The laser that could not work suddenly works better than anything designed to stop it. The mockery has ended. The revolution has begun. And the balance of power, built on the assumption that missiles could overwhelm any defense, has been shattered by a beam of light that costs less than lunch. What do you think? Can China adapt its offensive strategy, or has directed energy permanently shifted the advantage to the defender? Drop your thoughts below.